Hello everyone. My name is Sanjeev Kumar Pandey. I have completed my graduation in electrical engineering from BIT Sindri, Dhanbad, and after that I have also completed my master's degree in electrical engineering. My stream is machine drives and power electronics. I am interested in doing research related to machine drives, power electronics, converter designs, and electric vehicles. I have done a project in my M.Tech. I want to show it to you. So my project is a multi-level converter-based EV battery charger. My guide was Professor Suman Maiti in the Department of Electrical Engineering, IIT Kharagpur. This is my overall topology. My topology consists of two stages. First is AC-DC stages and DC-DC stages. We can see that in the AC-DC stages, it is hybrid modular multi-level converter. And in the DC-DC stages, there is two dual active bridge converter. That is, I have named it four port dual active bridge converter, or we can say it as quad active bridge converter. It is coupled by high frequency transformer. Let me show you my simulation results. This is my simulation results. I want to do basically three modes of operation, that is grid to vehicle, vehicle to grid, and vehicle to vehicle mode of operation. In the grid to vehicle mode of operation, we can see that the port 2 and port 3, that is the output port, the power is delivered from port 2 and port 3 very smoothly. We can see in the graph, and the phase shift, as I change the power level at 0.195 second, the phase shift is changing also, and before 0.195 second the phase shift is same, because the power level is the same for both the ports. After that, we can see that the voltage of the inverter and the submodule voltage, the grid voltage is also sinusoidal. The grid current is initially it contains a little transient, but after achieving on steady state, it becomes nearly sinusoidal. And we can see that the total harmonic distortion of the grid current is 3.04%. Now, this is the inductor voltage and current of all the ports, that is, all the four ports, two input ports and the two output ports. We can see that the inductor pulse is coming properly and the inductor current waveform is also nearly trapezoidal. Now my V2G mode. As in the phase shift of the G2V mode is in the negative direction, in the V2G mode, the phase shift is in the positive direction. In zero point 0.2 second, the phase shift of both the ports are different because the power levels are different. I have changed the power levels. Before zero point 0.2 second, the phase shift of both the ports are same. So port 2 and port 3, that is reference power and actual power, we can see that both are tracking properly. We can see that the grid voltage and grid current also coming properly. Inverter voltage is also proper. Submodule voltage, it contains a little bit of it contains a little bit of ripple of plus 10 plus minus 10 volt and plus minus 20 volt, but it is coming almost proper. Now we can see that the inductor voltage and inductor current are also coming properly at inductor voltage is generated at the pulse voltage of plus minus 200 volt, and the inductor current is also trapezoidal. Now the V2V mode, that is the vehicle to vehicle mode. In this mode, no grid is connected. We can see that the power is transferred clearly from port 3 to port 2 properly, and the power tracking and current tracking is also happening properly. And in the V2V mode, we can see that the voltage is not voltage pulse is not within 200, it goes above 200. That's because there is no grid side voltage, there is no grid side DC voltage of 200. That's why it is going above plus above 200 and less than 200. And the inductor current is coming properly trapezoidal. Now I also did transformer design. Let me show you the ANSYS simulation of the transformer design. Here, this is my ANSYS simulation where what I did is that I have did the magnetic flux density distribution, and as I have assumed the magnetic flux density to be zero point 0.2 Tesla, and the maximum magnetic flux density that I have got is 0.19 Tesla, which is up to the mark, means we can design this type of transformer also, and my assumption is correct. Let me show you my hardware. This is my entire hardware of HMMC. Actually, AC to DC sketch and DC to DC sketch, I have done the HMMC part, that is AC to DC sketch part hardware I have done. This is my entire hardware structure. Here we can see that the sub modules and the director valve, and this is my motherboard where I have used the DSP controller. The DSP controller name is TMS320F28379D. Here is my MCB from where I am getting the grid current. This is my inductor, and this is the single phase auto transformer. And here is the backside sub module capacitors, and this is the heat sink. And this is the rheostat, which is connected with the sub module capacitor for generating the load. These are my hardware results of the HMMC. This is the open loop results of the HMMC. This is the closed loop current of the HMMC. And this is also the closed loop current of the HMMC where some module voltages are also represented. I also tried to do the closed loop voltage control of HMMC. Due to lack of sorting algorithm, my sub module voltages are not coming properly, but this is my future scope of the work. So this is my future scope of the work: hardware implementation, efficiency calculation, improvement in ZVS, and comparison of the fuzzy logic. I have used the fuzzy logic control for my quad active bridge converter, and I need to compare the fuzzy logic control with PID control and model predictive control also. So this is my entire presentation for my M.Tech project. Thank you.